Hi, and welcome back to another lesson in the physics video series. Today we're going to be discussing dropping a ball versus throwing it to the ground. We're going to look at free fall acceleration versus free fall acceleration with an initial velocity. Let's get started. Whenever we solve a uniformly accelerated motion problem, it's best to have the reference tables ready, and today we'll be using equations 3, 4, and 5 in their various forms. Let's take a look at this question. On the left side, I have a question, and on the right side, I have a very similar question. On the left side, it says a ball is dropped downward from a height of 4 meters. Whereas on the right side, it says a ball is thrown downward at a speed of, say, 0.5 meters per second from a height of 4 meters. So the only difference between the left side problem and the right side problem is that the left side is a free fall problem, and the right side is a throwdown problem. Let's take a look at the solutions for both. We're going to ask questions. What is the impact speed? What is the time till impact? And what is the speed at the end of some random time interval, which we've chosen to be 0.7 seconds? This is the exact same question set on the right side. We're going to ask the same 3 questions, but we're going to compare the answers. We're also going to take a look at what equations we're using and how they modify or don't modify based on different initial condition. Remember, a free fall problem has an initial velocity of 0. Gravity is 9.8. But a ball that's thrown downward does not have an initial velocity of 0 because it has an initial downward speed. In this case, it's 0.5 meters per second. Let's take a look at how that fits into the equations. Finding the impact speed for an object that is freely falling is quite simple. We're going to use formula 5. V final squared equals VO squared plus 2AD. We know that the initial speed of any object that goes into free fall is 0. So we can then solve for VF by taking the square root of both sides. We get square root of 2g times the height above the ground. Notice I'm not using any negative signs here, because if we're heading down, that's a negative velocity, and gravity's negative. And since we're heading in the same direction as gravity, the 2 negatives cancel. So we'll just keep it positive right from the beginning. VF equals root 2gy. 2 is in the formula, g is 9.8, 4 is given in the problem. It's an initial condition. When you multiply and take the square root, you get 8.854 meters per second. So on the right side, we have the ball being thrown with an initial speed of 0.5 meters per second. So we still start with equation 5, except this time we cannot cancel out the initial velocity. It is not 0. It is 0.5 meters per second. So when we solve for v, we have the square root of VO squared plus 2gy. The original throw down speed is 0.5 meters per second, and that has to be squared, plus 2 times 9.8 times 4. So this equation is almost identical to this one, except this term didn't cancel out. And the final solution gives us a number of 8.868 meters per second. Unfortunately, because I have chosen such a small starting height, it's very hard to see the extra speed that it had, but you can see it 8.854 compared to 8.868. If I had let this fall, say, from a 100-meter building, and I threw this down from a 100-meter building, then you would really see a significant difference. The speed of the free-falling object is supplemented, as you can see, by the initial throw-in speed. When you throw the ball, not only does it have the speed that it has the acceleration due to gravity that comes with it. Let's now take a look at the impact time, or the free fall time as it's called. We know that the free fall time comes from the D formula. Formula number 4, D equals VIT plus 1/2 AT squared. For any object that is free falling, the VI is 0, so the D equals 1/2 AT squared. Solving for T, you get 2 times D divided by gravity. And this is what we have here. Time equals root 2y over g. So we insert the 4 meters for y and 9.8 meters per second squared for g. We take the square root of this, and of course we get 0.9 seconds. So anything that free falls from this height will impact the ground in 0.9 seconds. To find the impact time for something that has been thrown to the ground, you cannot use the free fall conditions. So you would not use equation 4, D equals VOT plus 1/2 AT squared. Rather, you would use equation 3, VF equals VI plus AT. and this is what you would get. Using equation 3 and solving this for t, we know that v final minus v initial divided by gravity will give you that time. So where do we get these numbers from? Well, v final was calculated in the step above, that's 8.868. And we know that the initial speed was thrown down with 0.5 meters per second, dividing that by gravity, and that gives you 0.84 seconds. So you do see that a faster speed reaches the ground in a shorter time. See, 8.868 reaches the ground in 0.84 seconds. 8.854 meters per second reaches the ground in 0.9 seconds. Let's take a look at what the speed of a free-falling object is, or a thrown down object is, at the same point in time after the release. For this problem, I chose 0.7 seconds. It could be any time from 0 to impact time, really. So let's take a look. We know from Formula 3, Vf equals Vo plus At, but in the free fall condition, the initial speed is 0. So we have gravity times time, and we're using 0.7 seconds. We have final speed of 6.86 meters per second. In the case of an object thrown down, it's still Formula 3, Vf equals Vo plus At, but the V0 is not 0. It's the original throwing down speed of 0.5 meters per second added to the acceleration duration, which is 0.7 times 9.8 meters per second, which gives you 7.36 meters per second. So it's obvious here that an object that you throw towards the ground will be faster at all points in its descent than an object that free falls. And here we have that comparison between dropping an object and throwing it straight to the ground. We can see that the impact speed for an object that's thrown is faster than an object that falls. We can see that the impact time is faster for an object that's thrown than an object that is free falling. And of course, at any point in the journey down, we can see that there will always be a greater speed for something that is thrown than something that freely falls under the Earth's gravitational acceleration of 9.8 meters per second squared. This concludes our lesson on the comparison of dropping versus throwing. I hope you enjoyed this video. Thank you for watching, and we'll see you in the next video.